Welcome everyone to this session called Living on Mars Beyond Surviving. This is part of the space track here at South by Southwest. And quick introduction to myself. I am Xavier Gastelier. I am an architect and I'm the head of design technology and innovation at Hassel Studio. I'm an architect, but I also have a bit of a fascination for space. Now, to talk about living on Mars and beyond surviving, I thought let's get some people together that really know about this subject much more than myself. So I'll introduce the three other panelists first, and afterwards we'll have presentations, very short presentations that will be about 5 minutes, and then we'll have a general panel discussion, right? So the first person I would like to welcome is Charlie Kamada. Hi, Charlie. Thanks for being here. Charlie is a space engineer and an actual astronaut who flew his first mission into space on the space shuttle, STS-114. And that was actually the first NASA's return flight mission following the loss of the space shuttle Columbia. He served as a senior advisor for engineering development at NASA Langley Research Center, and he's also the founder of Epic Education Foundation. Thanks for being here, Charlie. Second person is next to me here is Beth Healey. Dr. Beth Healey is a British medical doctor who overwintered in Antarctica as a research MD for the European Space Agency, stationed at spaceflight analog Concordia, also called White Mars. She the effects of extreme environments there. And last time we were going to bio of you is you were actually still a medical doctor in the Swiss Alps, but at the moment you work on the front line in the battle against COVID. That's correct. Then last, Rob Muller. Rob is a senior technologist and principal investigator in the Exploration, Research and Technology Programs Directorate at NASA's Kennedy Space Center. He is the co-founder of the NASA SwampWorks Innovation Labs, and he's also Kennedy's lead for autonomous robotic systems involved with in-situ resource utilization. That's a very long bit, a whole mouthful, but what I would like to say, Rob leads one of the coolest labs at NASA, where they are developing and designing the robots and the rovers that will hopefully one day construct infrastructure on Mars. Rob, thank you so much for being here.
Thank you, Xavier.
So we're going to do very quick, short presentations. It's going to be 5 minutes each. And what I've asked the panelists was really looking into, from your own perspective, from your own experience, what it would take for people to live on Mars, not just to kind of survive and cope, but really to kind of thrive on another planet. What would it take, right? It's a very simple question, and I'm sure you all have kind of different ways of kind of responding and talking about that. And also, so the 5 minutes, also take it as an opportunity to give a bit more background to yourself for the audience, right? I'm going to ask Rob to start first. I'll do the second presentation, and then we'll have Beth, and then we'll end with Charlie. Is that all right?
Okay, so thanks for inviting me to the South by Southwest panel. I'd like to talk to you today about NASA's journey to Mars. This is NASA's stated goal is to send humans to Mars. And the reason why is that Mars has evidence of previous life, and it's a very Earth-like planet. And in the past, something happened to Mars that changed the outcome. And so by learning about Mars, we can learn about the Earth, we can learn about the solar system. It has a lot of science potential. And it's also a place where humans can potentially live, because the environment is a little kinder than being out in the harshness of deep space. Next slide, please. NASA's strategic plan states, in a very first statement that you see in the NASA strategic plan, objective 1.1, it says, expand human presence into the solar system and to the surface of Mars to advance exploration, science, innovation, benefits to humanity, and international collaboration. So that's very important, is that is a policy, stated policy that we will be going to Mars one day. However, Mars is hard. It's a 6-month journey to Mars. You're committed to a 1.5-year stay, and then it's a 6-month journey back. So this is an incredibly difficult thing to do. It's a little bit easier to go to the moon. The moon is 3 days away. And so the strategy is to go to the moon as a proving ground, test out the technologies and systems, learn how to live in deep space, and then move on to Mars. Next slide, please. I'd like to tell you a little bit about myself and what I do. I work in a innovation lab called the SwampWorks. It's at NASA Kennedy Space Center in Florida in Cape Canaveral, where the rockets launch from. And this lab, I'm the co-founder of the lab, and I have a history in launching the rockets at Kennedy Space Center, and then first 15 years of my career I did that. And then I moved on to the International Space Station, where we assembled it and checked it out before it went into flight. And then eventually, in 2011, when the space shuttle program was ended, I formed a lab called the SwampWorks. It's an innovation environment, and the reason why is because we thought we could do things differently. We were trying to get back to the Apollo days, and this is an environment where we have lean development, a lot of prototyping, fail fast forward. We're not afraid to fail, and by iterating very rapidly, we can come to better solutions than if you slowly develop things with a lot of overhead. So this is a new way of working, but really it's not new because that's how they did it in the Apollo days. Next slide, please. This is a cartoon that was drawn by Alison Wilgus. She took a tour of our lab, and she got so excited by everything she saw that she actually made a comic book about our lab, and the link is there. And I just like this because it shows how excited people get when they come to our lab and how relevant we are to the future of space exploration. Our lab focuses on using resources in space, because if you go into space, that's really, you have no choice. You have to use the resources. It's very difficult to live in space, and the good news is that there are a lot of resources in our solar system and beyond in the universe. There's almost an infinite amount of resources compared to what we have on Earth. So this is a big opportunity for the human race. Next slide, please. What exactly are space resources? Traditionally, we'll talk about water, atmospheric gases, volatiles, metals, and these are contained in the soil on the moon, which is called a regolith, and regolith is the crushed rock covering the surface of the moon and other planets. But there's also non-traditional resources. Trash is a resource, waste from the crew is a resource, spent landers, residuals, these are all resources. And then energy is a huge resource. If you're energy rich, then you can really do a lot in space. So where you are in space matters, because if you have sunlight, then you have access to energy. It's also very cold in these areas. If you don't have sunlight, temperature swing on the moon is extreme. It can go from minus 175 Celsius to 125 Celsius. And even if you're standing half in the shadow and half in the sunlight, you'll have these extreme thermal differences that will cause large stresses, thermal stresses. It's also a vacuum, and that can be an advantage for manufacturing, but for humans, it's certainly a difficult environment. And we're in micro-reduced gravity. It's 1/6 the gravity of Earth. I've already talked about the thermal gradients. And so really, when you go to the moon or Mars, location matters. So it's like in real estate, location, location, location. And that's something I think we should consider when we talk about going to Mars. Next slide, please. When we go to Mars, we'll have to think about some constraints, and in selecting a site on Mars, these are the kind of factors that need to be considered in order to pick a good site. So where you are really matters. What the terrain is really matters. Topography and contours. This matters not just for construction, but it also matters for radiation protection. If you're in a valley, you'll have less radiation. If you're next to a cliff, you'll have less radiation. So you can use the topography and natural contours to your advantage. Just the dimensions and area and how big is your base, what is your master planning, these are all things that need to be considered. What the climate, there is a climate on Mars. They have a summer and a winter and spring and autumn, and they have the dust storms. They are dependent on the weather. And so this is a planet with an active climate. There's seasonal patterns in the sun and shade. Albedo is the reflection of sunlight off the surface, and that can have a lot of consequences for thermal issues. Radiation is there. There's two types of radiation. There's galactic cosmic rays and solar particle events. And solar particle events come from our sun. Galactic cosmic rays come from the background noise of the galaxy. But both of them are hazardous for humans, and they can cause cancer. So we have to consider that. There is also wind on Mars. There's very high velocity winds, but the density is so low that the dynamic pressures is 1/10 of what it would be on Earth. So it's not significant, the wind, but there is wind. There's glare and reflection, spacecraft-induced ejecta from launch and landing. These are all things that need to be considered. Next slide. And then when you're forming your decision on how to do the master plan for a Mars base, there's interactions between all these different elements. And so this is just a way of showing those interactions and the dependencies. And so I just would like to point that out, that it's not just one thing, it's many systems working together. Next slide, please. Now, recently, NASA had a competition called the NASA Centennial Challenge, and it was all about 3D printing with concrete. And this is where the construction industry, the architecture industry, this is how NASA can help, even on Earth. We fund development of technologies, we motivate the public, we inspire companies to have stretch goals, and that's what the NASA Centennial Challenge is all about. We had a head-to-head competition in April 29th to May 4th, 2019. And we actually had many teams apply, over 170 teams applied. Only 2 teams made it to the final. And these 2 teams were asked to build a 1:3 scale structure of an actual Mars habitat. And here you see the 2 competitors that were able to finish. It was AI Space Factory. It's a small architectural firm in New York City. And they were able to build this. So part of the design, part of the competition was coming up with an architectural design that could be 3D printed. And so AI Space Factory has this ellipsoid shape on the left. And then Penn State University, they came up with these conical shapes on the right. And that was quite exciting. And we think we'll have technology, robotic construction technology, which can be used on the Moon and Mars. And that is part of our future. And that's all I have.
Thank you, Rob. That was amazing. What I'll do next probably is I'll probably do my presentation. Everybody sees that? Yeah? All good?
Yes.
Good. All right. Okay, thank you, Rob, for that presentation. Well, it's great to come after you because I was one of the participants in Rob's Centennial Challenge, which was a great way really for architects and non-space industry to really get involved. Now, designing a 3D printed space habitat. I always think that astronauts really have kind of a rough deal, right? If you look at how astronauts have been traveling and living in space, it's not easy. It's not luxury travel at all. And Charlie, you can talk about that later maybe. And it really started, I think, with Yuri Gagarin. Because Yuri Gagarin, first man in space, he had a spaceship, Vostok 1, that couldn't even land, right? The Russians hadn't quite figured out how to land it. So he had to, when he came back into the atmosphere, he had to get ejected himself out of it and actually land by parachute himself, separate from the spacecraft. Right, that wasn't even known at that time. I think it came knowledge only a few years afterwards, and so that's a rough ride. I would really argue that we might have not gone that much further in that thinking. So this is the ISS. If you look inside the ISS, that's how the astronauts live there now, right? I don't know about you all, but personally, I wouldn't really want to live there for any long time, right? Astronauts are there now roughly for often 6 months, even longer. Going to Mars is going to be maybe 3-year missions. I personally can't see myself living in a space like this. I don't think many architects or designers were involved in actually designing this. It's a very much an engineered space. But I believe architects and designers do have a space in space. And I look a little bit at history for that. And I look at architects that have worked in space. This is Galina Balachova, the only Russian architect in the Soviet program, the only architect to work in it. And she was involved in designing the interior of the Mir space station. She was also involved in designing the interior of the lander, the lunar lander for the Russians that never flew, of course. And she was involved in designing the interior of the Soyuz capsules, orbital capsules. And I just love these drawings of her because they look very, very different to what you see at the moment in the ISS. You know, different materials. It's all much more tactile. It looks almost domestic, right? It's interesting. Another designer in space, Raymond Lowry, famous industrial American designer. I was the first designer involved at NASA. He was involved with Skylab, famously, the first really big orbital station from NASA. And the first time astronauts were actually living for a longer time in space. Raymond Lowry was involved in quite a few of the design bits in Skylab. But one thing I want to talk about and mention is he designed a window in Skylab. So you might think of, well, okay, a window, we see it in the background there, it's a window. Well, actually, he didn't really design the shape of it. He actually he made the fact that there is a window, because originally, the original design of Skylab, there was no window. But somehow they had to get a designer involved to actually convince the engineers and convince NASA, no. Astronauts are going to be for weeks and months in a space station, and they're not going to see this. That's just crazy for me, right? As an architect who designs for people, I think that's just a crazy idea. So I've learned quite a bit from these two designers. This is our design for the interior design for the Centennial Challenge. We worked with 6 modules. It's a very rational design. We looked at all the technical things. We looked at how this thing would be assembled, how it would get to Mars. We looked at how the systems would be assembled and together on Mars. It's a very rational system because we have like a radial system of racks, a rack system that is interchangeable between the different modules. We have a lab module. We use this radial system of movable racks as well on rails, which we think would actually save us a lot of space in comparison to what we have now on the ISS. You can open up a rack, you can do your experiment, close it up again, much more. The same system works for our workshop in our habitat. And if I then go to the greenhouse, again, that radial system with racks, movable racks. But besides this very kind of technical thing, interior bit, we also have to protect ourselves from radiation. And Rob really explained that really well. We have the solar radiation, we have the cosmic radiation, and that's where the whole interior is really encapsulated under this shell made out of regolith, which is Martian dust. So it's 3D printed shell structure, which we protect. We're kind of creating our own cave to protect ourselves from radiation. But taking all these kind of technical things in mind, we also wanted to make sure we create a space that is great to live in. Looking back at Bolasheva, looking back at Lowry, we use materials that are quite different. You know, we use some veneers, wooden veneers. Why not? Why not have more tactile materials, right? Also, why not have a bigger view? We have a big window here looking at the rest of the habitat and to the Martian exterior while still being protected and being very generous as well with space, because we're using inflatables. So we actually can expand on the interior space as well. And we didn't only do some renderings, we actually went out and we were invited by the Design Museum in London to go and build it for real. So this is a mock-up of one of our pods, including all our 3D printed furniture we have there. Again, we didn't bring that with us to Mars. We actually 3D printed on Mars from recycled materials. And in the background, you see the big screen, the big video screen that will give us that view to the rest of the habitat. It was kind of a VR experience that we created there. So we hope we kind of create a space that is maybe gives a different view of how astronauts could live on Mars. Okay, do you want to share your screen and start?
Okay, I'm sharing screen, keynote. So, hi, I'm Beth. Really happy to be joining you guys for South by Southwest. So I'm here to share some of my experiences of working at Concordia Station in Antarctica as the research MD for the European Space Agency. So this is my base, Concordia Station. So we're about 1,300 kilometers from the coast, and we're situated on the Dome Charlie Plateau. And we're actually at altitude at Concordia as well, so it's a little bit like living at the top of Mont Blanc for the year. So Concordia is considered a spaceflight analog by ESA, and the reason for that is twofold. So the first is that it's an extreme environment. So this was a screenshot that I took while I was overwintering there. And the first thing you might notice is that it's pretty chilly, so sort of minus 80 degrees centigrade. And also we have a really low barometric pressure as well, and that's because of the altitude we're at. And also during the overwinter, we have 105 days where we don't see the sunlight at all. So you can see my little light right next to the station there. And this was the picture that was taken around lunchtime. So it really is completely dark, sort of night and day. And so it's those two factors together, so the extreme environment and the long polar night, that means that the crew at Concordia are completely isolated, even in case of emergency for 9 months of the year. And this becomes really increasingly relevant to spaceflight as we're looking at going on sort of longer duration missions. So if we're currently to have a medical problem at sort of low Earth orbit where we're currently at, we can normally evacuate astronauts within a day or a couple of days. Whereas if we're going on to longer duration missions like to the moon or, for example, Mars, we're going to be going further away. And so the medical models that we might need and also the psychological pressures and challenges on the crew are also different. And there's a few other things as well which make Concordia really interesting and relevant to long duration spaceflight as well. So like in space, we're a small international crew, and this was actually the crew that I overwintered with. Was sort of a mix, we had 3 girls, 10 boys. We're a 50-50 mix between scientific and technical crew. And we're also what's considered a skeleton crew as well, which meant that our crew had to take on job roles above and beyond what we're down there to do. So for example, the plumber had to scrub in to theatre in case of emergency, and likewise I was part of sort of the fire rescue team and had to help out with mechanical jobs as well. We also, although we're isolated, we also sort of, you can't get away from each other as well, and that's a lot like long duration spaceflight too. So there's a lot of monotony in the crew environment. And there's also quite a lot of sensory deprivation. So we're actually on the plateau. So, you know, one of the main reasons I wanted to go to Antarctica is I love going skiing in the mountains. But if you're really into that, then Concordia is not the place to be, because this is what it really looks like in all different directions. And the sensory deprivation in terms of the crew that you're with. So I didn't see any old people or young people for 9 months. I didn't have any fresh fruit and vegetables. And you couldn't even make a snowman because the snow is just like sugar there. So it's a really weird environment to be in, and you don't have any sort of nature things, like you don't have any animals, you don't have any mud, so everything is super pristine, clean, and all sorts of things like that. And one thing I really noticed as well is not having any water to jump into, so you only had showers. And as soon as I got back to went back to New Zealand, I was jumping into lakes and streams everywhere because I hadn't been submerged in water for 14 months when I got back, which is something I wasn't expecting to be missing. So there's a few other things as well which make it like space. So we have water recycling facilities there as well. So we're trying to create a sort of sustainable life support system. And also, although this wasn't a project at Concordia, this is one that ESA run down in Antarctica, which is called Eden ISS, and it's all about sort of hydroponic growing of vegetables and sort of fresh fruit and vegetables, like again we're seeing in space as well, up on the ISS. We also had a requirement for remote telemedicine facilities and sort of remote communications, and this was really trialed and also developed in Antarctica. And it's also become increasingly relevant, of course, during COVID, with our need to sort of isolate from patients and infection control measures as well. And this was the operating theatre that we had in Concordia, and we're here doing a sort of test to a hospital in Rome to see how that worked. We also have really limited supplies as well, so we can only get things in and out of Concordia during the summer there, which runs from about November to February. So you have to be really careful to make sure that you have all the right food and equipment for all the scientific experiments, and also the medical equipment that you need as well. And you need to really think about what it is you might need so that you don't run out during your time there. And also just building the station. So at Concordia, there were a few sort of plane crashes, which is why we had to develop an overland traverse, which I was actually fortunate to be part of. And this is like a big overland land train, which goes from the coast of Concordia for the 1,200 kilometers to get all the equipment and supplies that you need. And we have about 2 of these running each summertime. And this is how you're able to build the station. So it really is building and sort of really extreme environment where you sort of really limited access to materials. And places and stations like Concordia really helped in the development of new Antarctic stations, but I think also in the future will help in the development as well for sort of future space architecture as well, because we've learned a lot from our experiences that we've already had down there in overwintering. And Halley is a great example where we've really used all the research and the experience of people working in Antarctica to really try and optimize the environment that Antarctic overwinter is living in now. And it's really exciting things to see, like the Halley station, and I hope that the same research and technology will be taken forward in our planning of sort of future space architecture as well. Okay, thank you very much for my presentation.
And I'm gonna give the word to Charlie.
Okay, so I'm sharing right now, and I'm gonna hopefully try to do this without messing things up. Those first 3 presenters have amazing slides. My slides are going to be very boring, typical engineer. Not, but what I'm going to talk about is something that I started working on probably the last 15 years of my career at NASA. And so, as you may have heard, I flew right after the Columbia accident, right? And so this was a very trying time. I was training in Russia when the accident happened. And I always hark back to this because really how I looked at NASA and where my passion eventually changed to was affected by this accident, right? People on the ground were looking at this large piece of foam coming off the external tank, hitting, it looks like the wing or the underbelly of the vehicle, very fragile thermal protection systems, the tiles and the wing leading edge. And the people on the ground that was supposed to be the experts had to make a decision. Was this going to be a problem? And the team on the ground said no. And without any real knowledge of the key disciplines needed to make that decisions, they emphatically said this was not going to be a problem. As a matter of fact, we probably don't even need to tell the crew. And we all know what happened when they returned from space. And so my point here is that we rely on some amazing people. We have this interconnected team of teams, people that are training to go in space, relying on people on the ground. And these people made a terrible decision. And so besides the technical problem, which they couldn't stop foam coming off the vehicle and couldn't determine why it was coming off the vehicle, the reason one of the accident investigation board basically said it was the culture that was one of the primary causes for this problem. And in particular, we had a psychologically unsafe culture at NASA at the time. But what I've done as I've been researching this problem and diving into the psychological behavioral science aspects of it, I've uncovered something that I think many of the other investigators failed to see. And it's because of my research background. I really believe the cause of many of these accidents is the fact that we do not have the right team of people analyzing the anomaly. Okay, they're not researchers. They don't know how to combine their different disciplines and look at these multidisciplinary problems. And so, what I'm going to talk about today is really the team of people we want on the moon and Mars, right? I mean, it's going to be very different when we go to Mars. They have to be autonomous, right? And so, I hark back to when I was a researcher at NASA Langley for 22 years. I grew up designing basically innovative hypersonic vehicles and the structures for these vehicles. And so we looked at thermal protection systems. Over my shoulder, you see a wing leading edge that was designed for space shuttle using heat pipes. And we attacked these problems as what Stanley McChrystal would call in his book, a team of teams. Basically, Stanley McChrystal basically said how we work together as a team and change the way we fight our enemy in Afghanistan and Iraq has to be totally different. And what I looked at when I saw it, when I read that book, was that's how we solve problems as researchers at NASA Langley. My small branch back then, the thermal structures branch, we had people with multiple different expertise in different areas: vehicle analysis, materials, structures, aerothermodynamics, and heat transfer. And not only that were they on our particular team in our branch, but we had researchers very close by at NASA Langley that had expertise down and in material science. So if we needed to pull those experts, we could go and reach out to them. And so how do we create this team of teams using technology now is something that I think is going to be very important for future teams of astronauts on the surface of Mars. How they interact and solve problems as a team, how they interact with a time delay of 20 to 40 minutes with the team back on the ground is very important. And so I've been spending a lot of time working on ideas for how to do this. You know, one of the things is this is a graph that a schematic that basically shows that information is doubling almost every 12 hours, according to IBM. Several years ago, it was every year, right? And so we have this, we're inundated with knowledge, right? And so how do we, as a high performing team, basically go through this morass of information? How do we rapidly search and find just the right content or just the right person to bring them into our team to solve these problems? Not only that, but we have to train and constantly learn, retrain, learn new skills while we're on the surface of this planet. So, how do we accelerate that training for those teams when they're out there? How do we take advantage of technology? When I was training as an astronaut, we used technology, we used VR, we used simulation so we could run robotic dynamic simulators of how the robotic arms would move. And thanks to the engineers and the scientists that developed this technology, it simulated very well the real environment. Okay, so, so one of the things we're looking at is intelligent knowledge discovery. You know, in all these different bodies of knowledges, these communities of practice, as we're building these systems that astronauts are going to operate, if you think about it, we can collect all the information of all these designers, the laboratory information, the test information, and now how do we use artificial intelligence, machine learning to help us curate that knowledge so now we can make it very searchable for the teams that are going to be using that information. We're looking at developing digital assistants. We're calling them team bots that basically not only monitor how the team is behaving. Are they behaving as a psychologically safe team? Are they sharing information properly? Are they connecting with the right experts? What are their behaviors, what are their attitudes, and can we use that information to help in their search for information to help them solve problems? So this is how we could take advantages of using computers and science and technology with the teams that we bring to space. Okay, and so uh, so how do we advance learning in space? We've been doing some research with the chief learning officer at Boeing, who has Boeing has what they call the aerospace program, which is one of the most one of the greatest capstone programs for seniors at university. And it's all a build fly. They go through a prototyping, a phased A to E approach for product development. And at the end of that process, they design and fly a UAV. And they do this with teams of students in multiple different geographically dispersed locations. Very similar to how multinational corporations operate. So now we're able to monitor how those teams perform, how they access information, how they learn, how they innovate and solve problems. So we're conducting research as these teams are working on these challenges. So when you think about, you heard a little bit about Beth and Rob talking about teams of people in extreme environments. We could be collecting tons of information, so we select the right teams, right? And we could teach them how to learn and accelerate their learning. And so one of the things we do, we access these teams of students, and this is just some preliminary information that we collected several years ago. And we looked at these two teams, and just monitoring very simple parameters, we can identify which teams were higher performing than other teams without really diving in and analyzing what they're talking about, natural language processing to do that, but just by looking at the types of communication, frequency, the energy, the engagement of those teams. Are they all talking to each other at equally distributed energy? Are they going outside their team when they don't understand something to bring other people in to help them solve the problem? And with just this very simple information, I was able to identify Team 3 as being the team that was going to come to this fly-off competition, was going to totally blow away all the other teams, and they did, which was amazing. And so my last slide talks about how we digitally transform the people that we train, how we train them, but more importantly, the skills that they have to have, what we're calling fusion skills, where the humans and the machines. We're not artificial intelligence, I think, is a myth. The only intelligence you're getting is when you have humans in the loop. And it's those humans being able to train humans to help teach the machines as we go along in these environments. So we have to send people in these environments that have to work with robots like the ones Rob and his team at the Swamp Works are developing. And they have to do this seamlessly. And so when we talk about astronauts of the future, astronauts that we want to send back to Mars, I know ESA is opening up and they're going to be selecting astronauts in the future. You know, there are certain skills we want to have, certain mixes of skills we want to have on that team. And so I think that's going to be very important for the survivability of that team. The type of work that we choose for our astronauts to do, whether they're healthy and happy, not only their environment, but the type of work is very important. It has to be meaningful. And we have to be able as human beings to exercise that right side of our brain, that creative side of our brain that really brings us joy when we're in these extreme environments.
All
So,
right. Thank you everyone for all these kind of short, snappy presentations and to kind of see all your backgrounds and what how that all feeds back into hopefully one day living on another planet, right? I'll have a few questions for you all, and I'll have a few, but then we have like maybe a loose conversation as well. One thing I always think about when think about living on another planet, and I compare it to spaces such as the International Space Station or living on Antarctica. The ISS is somehow still subdivided in different parts connected to different agencies, right? There's a Japanese part, the European lab, there's the Russian, the American, and even in Antarctica. Although Beth, you were on a station with an international crew, Antarctica itself is actually subdivided like a massive pizza slices, right, to different nations.
Yeah, totally, yeah.
Right, yeah. So I always wonder, are we going to do that when we go to the moon or when we're going to Mars as well? Are we going to keep this silly thing that is these kind of, bits of places where we come from on Earth? Are we going to take this with us when we go to Mars or to the moon, you think? Well,
No, I
that's
second that really as well, because in Antarctica, as you say, all the different stations do have different nationalities, apart from perhaps uniquely Concordia, where we do have sort of multinationals. But there was still a lot of collaboration between all of the different stations, things like the sort of Antarctic Film Festival and all the different stations talking to each other. And I think that was really quite special, having that sort of interaction, as you say, between different communities and different cultures as well. And I think having sort of multicultural station also brings its own challenges, but also has a lot of rewards as well. And I think that was one of the best parts about being at Concordia, so I got Christmas Day the wrong day, because in the UK it's like the 25th and everyone else is celebrating it on the 24th, and I didn't even realize when I woke up that day. So just like little things like that, you're just like, oh, okay. And so we just learn from each other, and I think that's a really special thing that I took from my experience, and I think also it's really relevant to spaceflight as well.
That's great. Other question I have was, now, Charlie, you look at teams and how they are structured to solve problems and to kind of, have creative sides in there as well, and people with different skill sets all working together. And Rob, you've been, you were organizing this Centennial Challenge, the 3D Printing Habitat Challenge, which opened up really the field to people like myself who are not used to space engineering. So it's opening up these fields I find really interesting. So question for you, Rob, like what have you learned from opening up the field to kind of, people that are not used to working in a specific way? What was the thing that surprised you the most?
Well, I like working with architects because they have more of a right-brained approach to the problem. They start with sketching. They start with ideation. And what's really interesting about working with architects is they always pick something that inspires them, like an animal or a flower or a mountain, and they pick something that evokes emotion and also has functional relevance. So that's a different approach. In engineering is very dry. You're given a set of requirements, you decompose the requirements, you work the requirements, and you build the product. I enjoy working with architects because there's more creativity involved, and they start with this more artistic look at things. But at the end of the day, they have to build a good product. So what I learned from working with the architects was that if your requirements are wrong as an engineer, you're not going to get a very good product. And sometimes the requirements were difficult for us engineers to work with. One time we were on the rules committee, and an architect said to us, we have a new rule. I said, what is your rule? He said, we're going to score the level of delight. And all the engineers in the room, their heads started spinning. And we had a mass revolt from the engineers saying, we don't know how to score level of delight. What is that? And the architect said, it's whatever we feel. It's the level of delight. And we had a rule for level of delight that we scored. And the engineers really had a hard time with that. So that's the kind of cultural issues we're dealing with.
I could probably talk a little bit about an anecdote. In my own experience, a few years ago, Rob, you were really kind to invite me to at a Keck Center of Space Studies in LA, and it was a workshop, it was like a week-long workshop around in situ resource utilization by 3D printing, and the room was really full of NASA engineers, and I must say I felt a little bit out of touch. I really felt like the dumb one in that room, and we had some workshops, small teams working together, and I was like, I didn't know what to do really, because people were talking about certain things about Delta V and all sorts of things that we were going to be imagining new missions even, and I didn't know what to do. But at some point, after about half an hour, I figured out what to do. And what I did is I just started drawing. I started drawing what I thought the engineers and the space scientists were talking about. And somehow, by drawing, it was quite interesting. The discussion started to be a bit more directed and a bit more, by me drawing what the engineers were saying. And they were like, no, it's like this. And then suddenly the conversation started to happen more. So it was somehow, I was like the drawer of the day. Which was an interesting place to find myself in. So yes, I do think there is much more collaboration needed. I feel.
Xavier, I think what you said is very, very important. We invited people that were architects, right? I think the real innovation happens when you bring people with different backgrounds to come in and look at these problems. So I run a nonprofit, the Epic Education Foundation, and we teach kids how to be innovative, and kids of all ages, even old kids. And so we look at these very young students that were not taught how to do things, and their ideas seem crazy. But then when the graduate students and the senior people start looking at these ideas, they're not so foolish. The other thing is that in the return to flight, a lot of people said to me and the teams of people I was creating to solve these problems that what we were doing was impossible. And so when you have people that have been working in a narrow area for a long time, their field of view gets very narrow. They don't go back and retest their assumptions, right? You're in these extreme environments like Beth is talking about, that brings out the creativity. And what you find out is that what people with the PhDs would tell you is impossible, you'll find out is possible. And so I think that's kind of the beauty of it. So I think it's good that NASA invites architects, people from many different disciplines, to solve these problems and to make it as diverse as possible.
Xavier, I'd like to plug the Centennial Challenges program because the 3D printed habitat for Mars was very successful. It made a lot of impact, had good press, and it opened people's eyes. But now we have a new Centennial Challenge called Break the Ice. And Break the Ice is all about what's changed on the moon is and Mars too, is we've discovered water. And when people say, well, what's the most important resource in the solar system? It's water, because water is not only the key to life, it's also the key to propulsion. So imagine having a highway system without any gas stations, no petrol, no gasoline. This is what we have today. We have a highway system in space with no fuel or no propulsion, no propellants. We have to bring the propellants to the gravity well of the Earth. Imagine if we could source the propellants in the solar system, and we call it a network of transportation nodes, which is the same as a highway with gas stations. And imagine if we had a gas station on the moon, a gas station on Mars, a gas station in the asteroid belt. Suddenly the solar system becomes accessible. And so this is why resources are so exciting.
Yeah, exactly. That's a good analogy, Rob. There, I like that. Yeah, you talked about the Centennial Challenge that was very successful. Then we made a video of our entry, put it on YouTube, had loads of comments, and there were two types of comments that kind of stood out for me. Well, first of all, there were all flat earthers talking about stuff that didn't believe anything. Not going to talk about that. But there was a second question or a second comment, which always comes back, and I think it's a comment that has been made even in the Apollo era, and I'd like to, Rob, you kind of alluded to it a little bit already, but why? Why should we go to the moon? Why should we go to Mars? I'd love to kind of hear that from each of you. Definitely Beth, because you were planning to become an astronaut maybe, so why?
Well, for me personally, I guess that was the biggest thing that I took from my experience in Antarctica was, initially I was a little bit put off by the idea of sort of working for space agency. I come from a background where I hadn't really had much interaction with space, and I sort of, it's a little bit daunting to apply for a job with ESA, but actually I had a really positive experience, and I guess the most positive thing that I took from it really was just how applicable all of the experiments that we were doing in Antarctica were really relevant to sort of clinical applications back here on Earth as well, in sort of the medical field. And I've actually since become involved in a sort of working group which is between like UNOSA, which is like United nations space. ESA and also a number of other sort of space organizations, say NASA, for example. And we're really looking at how you can address all of the SDGs, the Sustainable Development Goals, using space technology. And the group that I'm working in is looking at healthcare, so SDG 3, which is like good health and well-being. And I think it's really exciting to see how all of the space technology that we've developed can be used in sort of a healthcare environment as well. And so that ranges from obviously sort of medical applications, medical research, but also a whole range of stuff in terms of like satellite applications as well. So sort of predicting mosquitoes and sort of their habitats and how that's going to change with climate, to be able to put in like preventative programs, so like vaccinations, for example, in sort of malaria-prone countries and stuff like that as well. So I think that's really, for me, what the most important thing is I think having a goal of going to the moon or the Mars really inspires people to sort of develop tools and technology to get us there, which we can then use back here on Earth as well. And I think that's what's so exciting about it all.
Yeah, bring it back, bring the knowledge and technology back. Charlie, why do we need to? Why not solve the problems here on Earth first, and bring all the effort to going to Mars and the moon?
Yeah, I guess I'm one of the few panelists that was around when John Kennedy gave that famous speech at Rice University. We do these things not because it's easy, but because it's hard, and it's exactly what Beth and Rob and we've all been discussing. You're in these extreme environments. It forces you to rethink and be creative in how we solve these problems. But more often than not, the technology we're developing comes right back to help us here on Earth. The climate science that we're using, the satellites that we put up, just the fact that we have to sustain humans, we have to reuse, recycle in these environments is creating new industries, new technology that we could go back and design better cities, better transportation systems, better power systems here back on Earth. And so I think it's for all those reasons. It's a lot of fun to go to space, but it also challenges us, the computers that we develop and the technology that we have to develop to live in these environments.
No, exactly. I think Rob, why go?
Carl Sagan had this expression, pale blue dot. And where that came from was when Voyager went out, it kept getting further and further away from the Earth, and the pictures kept coming back. And there was one moment where when the astronauts in Apollo were on the moon, and they took a picture of the Earth from the moon, and that started the environmental movement, arguably, in the 1960s and 70s on Earth, because there was context. The human race suddenly had context for what this really is. It's a miracle. The Earth is a miracle. That's why we haven't found very many Earth-like planets. They call it the Goldilocks planet. It's not too hot, not too cold. We have water. We're in the right place. We're in the right orbit. Without a moon, we wouldn't have the tides. Without tides, we wouldn't have life. We are a miracle. So let's appreciate what we have, first of all. Then let's zoom out and consider ourselves as a pale blue dot in a vast, vast universe. We have a beautiful planet. It's truly an amazing planet. So our job is to preserve that planet, first of all. Second of all, the resources are not on this planet. The resources are in space. If you go into space and you start using the resources in space and you have self-replicating machines, there's exponential growth in space. The Earth is a beautiful place. Let's live on it, and let's put all industry in space, robotic. It creates all the wealth we need, and we have a good life on Earth. This is not my vision. This is a vision that is shared by many people, and including Gerard O'Neill, who started all this in the 1970s, and Jeff Bezos has signed on to this vision. This is really our opportunity, is to use the resources of space to create the wealth we need to sustain the human population in a responsible way. And that's our opportunity. We can take it or we can leave it.
Thank you so much for this call. This was really exciting to have you here. It's a shame we couldn't have done this in South by Southwest in Austin, but I'm sure we'll kind of get together at another time. but then again, we're probably going to reach a much bigger audience, and I think that's one thing that the result of this pandemic, they were just reaching more people, and I think that can only be better, right? So again, thank you all for amazing talks, great discussion, and I hope to see you all soon.
Thanks, Xavier.
Thank you.
Great meeting you, Beth.
Yeah, you too, guys.
See you, everyone.
Thank you. Have a good conference.